Okay, welcome back. We're going to do the age, this time using the Julia language instead of the MATLAB language. All right, so let me start up Julia. All right, so here I'm going to do Julia stuff. In this directory, I have the file transport operator.mat, and we're going to load that file into Julia, and it contains the advective diffusive flux divergence operator on a model so it's the OSIM model. Okay, so Julia is not as smart as MATLAB, so we need to tell it something. So using a mat, that's going to tell Julia how to read in the MATLAB file, because the transport operator was created in MATLAB. We need some linear algebra package, and the sparse arrays pattern, and then the print package. I think it's called printf. Okay, and then we want to change the local path, dir name, to where these files are. File, like that, and mat file is equal to mat open. So mat open is part of the mat package. How to open a MATLAB file, transport operator.mat. All right, so let's try it to make sure this works. Include homework.jl. See if it works. Undefined IO stream. Let's see if I can read or x grid is equal to read map file grd. Yeah, okay. So I can read in. So grd is a structure in MATLAB, or a dictionary in Julia, that is inside this transport operator.mat file, and it contains these variables here, dA, y, dv, and so on, that define the grid for the on which the advection diffusion operator, or the tracer transport operator, has been discretized. So the volume of all the grid boxes in this dv variable, so they're finite grid boxes. There's it's a 2-degree horizontal resolution, so there's going to be 180 longitude, 90 latitudes, and 24 depth levels. So we can read in a few more variables, and then we can talk about them in a bit. So mat file, and then grd is equal to read mat file of grd. Mask is equal to read mat file of mask. trdiv is equal to read mat file of trdiv. So trdiv is this flux divergence tracer transport operator. It has dimensions or units of inverse seconds. So dimensions of inverse time, units of inverse seconds. So it gives you the divergence of the flux of tracers, which will have the dimensions of inverse time. And it's in seconds, so I'm going to convert it into per year. So I multiply by the number of seconds in a year, 365 times 24 times 60 squared. Okay, and then what else do we need? iwet, which is the indices of the grid boxes that are ocean points. So in mask is going to be a 3D array, and there'll be ones and zeros, ones for grid boxes that are wet, that are either ocean points, and zeros for grid boxes that happen to be in the continent on the land. So iwet is going to be read mat file iwet, and what we want to do is we want to make this into a column vector, because it's a row, I think, from MATLAB. I'm not sure how it reads it. In any event, and then we want to convert into an integer, because MATLAB stores everything as doubles. So int 64, like that. And idry would be the indices, which I'm going to convert to integers, of the dry grid points. We don't use that variable, but I thought I would just read in so I can show you. Colon like this. Alright, let's see if I could run that. Include, and then length of I wet. Yeah, 191,169 wet grid boxes. The length of I dry, 197,631. So if I add those, length of I wet plus length of I dry, I should get 190 latitudes times 180 longitudes times 24 vertical levels. I get the same number. Alright, and then I'm going to extract from grid the latitude and the longitude. So the latitude is y is equal to grid dot y, and I'm going to make it into a column. And then, oh, and this is a dictionary, so it goes like this in Julia, not a dot. Grid of y, like that. And x is the longitude, grid x colon, like that. Okay, and now I think we're ready to start solving for the age. Alright, so I'm going to put some comments here. Alright, so the partial differential equation for the age, I don't know if this word's partial. Yep, partial A slash partial T plus nabla div C dot left bracket U times, if we're going to do a boldface, U, E, F, E, F, U. Oh yes, E, F, U. Star A, which is A. So this is, UA is the advective flux, and then I add the diffusive flux, which is minus the diffusivity times the gradient, so minus K, I'm just going to use kappa, looks nicer, nabla, so that's grad, nabla of A is equal to 1. Alright, so it tells us that the transport of the age is a conserved tracer, except that there's a source, or it's a conserved tracer with a source, and the source is 1 year per year. So every year we age at a rate of 1 year per year. Now, for the 8 water partials, some water partials are die or they're born, and that happens when the water is in the top layer of the model. So when the water touches the surface, then it instantly, its age is reset to 0. And so we have a boundary conditions that A is equal to 0 at Z equal to 0. And everywhere else, the boundary condition is that the diffusive flux A is equal to 0. So on all other boundaries. On all other boundaries. Alright, so we want to solve this equation for the age, but we're going to do it in this discretized models with finite grid boxes. And that means that we're going to apply the boundary condition not as a right at the surface. Instead, what we're going to do is in the top layer of the model, we're going to restore the age back to 0 at a certain rate. So we're going to do it at a rate of 1 per day, so frequency of per day, which is fast enough compared to circulation that it will clamp the age to 0 in the top layer of the model, and then as we go deeper down, it'll get younger. So the discretized version, dA dt plus tr div of A is equal to 1 plus this restoring term, or minus R times A. And R is this restoring operator, so that doesn't exist, we need to create it. So we're going to create R as follows. First, we're going to make a mask 1, which is going to be equal to the original mask, which we didn't read yet. Oh no, we did, yeah, the original mask. And then we're going to reset the value of this mask to 0 for all levels below the surface. So reset the value, and then we're going to make R to be a diagonal matrix populated by the value of mask 1 down the main diagonal. So SP diag M, a sparse diagonal matrix. 0 means the diagonal. The zeroth diagonal is the main one. Diagonal 1 above is the first or diagonal 1 is the one above the main. Diagonal 2 is the one 2 above. 3 is one above that, and so on. And then diagonal minus 1 is one below the main diagonal. Minus 2 is 2 below, and so on. So in this case, we want a diagonal matrix that is going to be ones for the rows and columns corresponding to the surface grid boxes where we want to restore the age back to 0, and then 0 everywhere else. So we're going to populate it with MSK1 of I wet, like this. So this will create a matrix n by m, where n is the length of I wet. All right, let's try it. Make sure there's no bugs. So include homework 4.jl. Oops. And I don't know if that worked, but it seems size of R did not work. What's R? Include, oh, I did the homework 4. I should have done homework.jl. All right, so I have an error. Over here, mask, where is that? Yes, so here in Julia, I want to vectorize this, so I want to do it for each and every element, so I need to put the dot. Okay, let's try it again. There we go, size of R, same thing as the size of trdiv. Perfect. Well, we don't know if it's perfect, we'll see when we try it if it works. Okay, now we want to solve for the age. We want to solve this equation, right? So if I'm at steady state, that means that dA dt is equal to 0. So the water is going to keep getting older until it comes back to the surface, then it gets reset to 0. And after the circulation has circulated, the particles have circulated a few times, it's going to reach an equilibrium state where the age will stop changing with time. And every grid box is going to have the mean age, or the mean time, since the water in that grid box was last in the top layer of the model in contact with the atmosphere. And so dA dt is 0. That means that trdiv plus r times a is equal to 1. So if we want to find the age at equilibrium, we're going to solve this system of linear equations. So there's going to be 191,169 equations in the same number of unknowns. And that seems overwhelming to try to solve, but the computer has no problem doing it in a few seconds. So we're going to create the matrix M, which is trdiv plus R. Oh, but R is a restoring operator, so I need to give it a time scale. So I'm going to give the time scale to be 1 day, which in years is 1 over 365. So all my units are going to be in years now, so 1 day. So R now has units of per year, the same thing as the flux divergence operator trdiv is now per year. If you look at the equation, 1 is just a pure number, it's in years per year, but age is in years, the 1 over dt and the ddt is in years, so the whole thing is dimensionless. dA dt has no dimensions. And same thing as this term, this flux divergence of age is going to be dimensionless because the transport operator has inverse years as a unit and a is in years. All right, then I need to make the right hand side. The right hand side is going to be 1s of n, and then I will solve for the age. So the first thing is I will initialize an array, a 3D array, the same size as the mask, and I'm going to set all the values to nans. And then I'm going to replace those values of A, which happen to be wet grid box, by the solution to this equation. So the solution to that is just m backslash right hand side of I wet. Yeah, right hand side, that's correct. And then we can make a plot of that. So I'm going to try a contour plot. Contour. Oh, I need the plotting package. Up here, comma, plots. Contour F. open parenthesis, x, y, a, colon, level. I'm going to set level to 9. So we're going to do the 9th level. Save it and run it. And then we wait. And it's slow the first time. Well, but because there's a bug, no, but it's slow also because that's the first time we use the plotting package. Alright, so let's see what we have here. No methods matching plus. So here we added the NAND. Again, I need to put a plus. Let's try again. Should be faster now because we've already, it's the second time we use the plotting package. And here's the window for the plot. And this gives us a plot of the age at level 9, which is level 9, that's Z lev. No, Z doesn't exist. Does Z exist? Oh, I didn't read Z. So let's read in Z. Z is equal to grid Z colon grid Z lev. That doesn't, oh, it's not how we do it. I get mixed up between MATLAB and Julia. What's that little quote there? It's annoying. Grid Z level. It's a 501.4 meters. So let's put that level into the title. So I'm going to create a title. String is equal to sprintf of age in years at depth z equals percent 5.1 f meters. That's a formatted print, and we're going to put in z of lev. Alright, so it's going to print it with 5 spaces, 1 space for the decimal, 1 space for the period, 4 spaces for the numerical value, the age, the depth, sorry, the depth. Alright, then I can comma, x label equals longitude in meters, y label latitude in meters, and title is equal to string. Save it and run it. sprintf not defined. Oh, I need an at. Excuse me, at. Try it again. And I should have a plot somewhere. I don't know where it went. Where did that plot go? Exit and start again. Shoot. Julia. I'm gonna wait again for all those packages to be compiled. Alright, that looks good. So we can see here the age at 501 meters. You can see the downwelling regions where there's Ekman convergence. So the westerlies wind in the southern hemisphere, the Ekman transport is to the left, and so you end up having convergence and then downwelling in these latitudes over here, and same thing in the northern hemisphere. And you see the older water where there's downwelling, younger water that's been near the surface very recently. You also see the North Atlantic is much younger than the North Pacific. That's because there's deep water formation in the Labrador Sea and Greenland Sea. And so water convects in the winter and then flows southward. And the western boundary current carries this water southward, and there's a lot of mixing with this younger water. Then you see the older water. So there's westerlies in the southern hemisphere. The Ekman transport is to the north, and so that causes a divergence along the continent, and that sucks water up from below, and the deeper water is older, and so therefore you have a band of older waters along the ACC over here. And then there's equatorial upwelling also. The Ekman transport, you have easterlies along the equator, and in the north, the easterlies gets an Ekman transport to the right, which is to the north. In the south, the Ekman transport is to the left, which is towards the south, and so you have a divergence, and that sucks up all older waters from below, and so we have older waters in the tropics. And then you have the oldest water in the subpolar gyre of the North Pacific. We can try it again, picking a different depth. So let's try level 15 and run the script again. Oh, I think I just killed that plot, and I don't think I can bring it back. I don't know why the plot doesn't come back. It's very annoying. Maybe if I do display. Let me try that. PLT is equal to. Save it. Run it. Display PLT. Does that bring the figure back up? No. It's kind of buggy, huh? Every time I kill it, it's gone forever. I have to remember to minimize and not kill it. Okay, so now we see the pattern of age at a depth of 1,500 or so meters, and we can now see that the Atlantic water, that's the depth of the North Atlantic deep water, which is flowing southward, is very young. It's been in contact with the atmosphere recently, so it's less than 200 years old. In the Southern Ocean, you're close to the deep convection from the southern, along the coast of Antarctica, and a mixing of the North Atlantic deep water. So you have intermediate ages, around 500 or so years, and then as you flow northward in the Pacific, the waters get progressively older until you reach the North Pacific, where you have the oldest water that are close to 1,200, almost 1,300 years. Okay, let's calculate now. I'll try to calculate the globally averaged, volume-weighted average of the age over the whole ocean. So that can be done simply by doing a volume integral of the age. So we sum the age in all the wet grid boxes, which we then, first I need to extract the volume. So dV is equal to GRD dV, colon, like this. And then I'll sum the age in the wet grid box multiplied by the dVs, dot star dV, colon I wet. So this is a volume integral over the volume of the ocean of the age, and then to get the mean I divide by the integral of the volume, so sum of dV of I wet. Let's hope that works. And I get 623 years, so that's the mean age of the water in the ocean, meaning that on average, if you pick a water parcel, it hasn't seen the atmosphere for about 623 years. So that means that most of the ocean doesn't know about any of the anthropogenic CO2 emissions since the Industrial Revolution. Most of the ocean doesn't. The water closer to the surface, it's had a chance to see the atmosphere, so there will be some imprint of what's been going on chemically in the atmosphere since then, but on average the water has not yet seeing the atmosphere. Okay, that was how you do a volume integral. Now I'm going to try to do, without killing this window, a plot of depth versus latitude in Julia. So I dread doing it because it's hard, because I never remember the commands. But let's try it. Where am I? Title like this. Alright, so string, I'm going to start and just copy what I did before. At sprint f age in years at %i. So this is a formatting for an integer. Degrees east. So we're going to plot a cross section at 200 degrees east. So starting from here, we're going east, 200 east, or 160 west. Okay, 200 degrees east, which will be the 100th grid box in the model because it's every 2 degrees. Comma, and I'm going to put longitude here. And I'm going to compute longitude is going to be 2 times k, or j, and then j is equal to 100. So the 100th grid box. All right, that's going to be the title of my plot. Then I'm going to do plot is equal to contour f, and then the x-axis will be the latitude, which is y. The vertical axis is going to be the depth, so that's minus z, and I think the plotting package wants the z to be in increasing order. So that means I have to start at the end, which is the bottom, minus the deepest level, in steps of -1 back to the surface. Then I put the age, A, and I'm going to plot all the latitudes, the jth grid box for longitude, and then all the depths. And then this, the size of this, so if I do size of A of colon 100 colon, it is a 90 by 24. So the first index is running the fastest, and I want the first index to be the latitude, which would be the second one. The first one should be the vertical one. So I'm going to transpose this array, transpose, and then another annoyance is that since I flipped the orders of the z's, I need to flip the order of the z indices. So I'm going to go from the end, steps of -1 back to 1. All right, let's try. Oh, and then I would put in x label is latitude in degrees, y label is equal to minus the depth in meters, and then the title is equal to the string, which is the age, this formatted string. Save it and let's run it. Let's bring up my picture again. And I didn't kill it, so hopefully it'll work and I can plot on top of the old figure. Include homework, homework.jl. Success. So we have latitude, depth, or minus the depth, the age, and that's at 200 degrees east. And we can see that in the southern ocean, southern hemisphere, the water is younger because there's deep convection. We're in the Pacific, right? And then as we go north, the water gets older. So you can see the Antarctic bottom water filling the bottom, and then it upwells, and so you get the oldest waters at mid-depth because there's going to be a balance between water from diffusing downwards from above and diffusing upwards or upwelling from below. And you can see the bowl of the gyres, right, the subtropical gyres, where you have Ekman convergence and downwelling with relatively young water. All right, What else? Oh, let's try the same thing now since it works. Let's pick a longitude in the Atlantic. So if I plot contour F of A colon 10, let's say 10th level. Right, so here's our horizontal map again, and we're going to pick a longitude that goes through the Atlantic. And so I think grid box number 165 goes through the Atlantic. So let's change J to 165, and let's run it again. Oh, did I kill the plot? No, I didn't. Good. Okay. And include homework. Yeah, and here's the figure. Let's see if I can stretch it. And so we can see the ages in the Atlantic are younger, right? The oldest is near the Southern Ocean, around 600 or so years. So deep water formation in North Atlantic is relatively young. It flows northward, aging as it goes along, and mixing with deeper and older waters from below. And then it upwells in the southern hemisphere, where there's a Ekman divergence that sucks water up from below. So you bring up these old waters to the surface, and then the Ekman transport is northward, carries that younger water, which then subducts in Antarctic intermediate water of the intermediate age. All right, so that is how we compute the age in Julia.